Hello and welcome back. Now, before you think I've gone completely insane, just hear me out. So what I want to talk to you about today is actually a legitimate electronic circuit. Now, I was not put in charge of naming it. I personally would have called it either a mechanical switch mode power supply or simply a power supply. But somebody else gave the name of a vibrator. Or it is known in technical literature also as a chopper supply. So if you're curious about how you can build your own vibrator, what you can use it for and what was it historically used for, one of its uses at least, and also many other things, then keep watching. So I was looking through this book with old radio schematics. And one of these stood out to me. That being this schematic. So what's so special about this? Well, one of its particularities is that this is made only for long waves and medium waves, not for short waves. Also, it doesn't have a variable capacitor. It has a triple variable inductor, which is quite odd, but this was used in certain cases. But the thing that's most special, or at least that stood out most to me, was that this thing is supplied from 12 volts. This is a car radio, a radio designed for automobiles. Yet it uses vacuum tubes that need high voltage supply, 250 volts, or around that value anyway. So how is this thing supplied? How is the power supply built for this in the age before transistors? How did you build its booster? Well, it has this thing, the BP9 supply block. Basically, this is what today would be referred to as a forward converter. It has an oscillator, transformer, rectifier, and then some filtration. And this turns 12 volts into 200, or somewhere around that value. Yet it doesn't use any semiconductor components. It has this thing. So what's that? I mean, it's not some regular component, it's something a bit special. This is the vibrator. So to understand how the vibrator works, we need to first understand how an electromagnetic relay works. Now what I got here is a modern day relay. Basically, it's a black box with some pins on the bottom. Looks like a capacitor. I mean, nothing interesting going on here, nothing really nice to see. Now what I got here is an old relay. This is from 1982. And this time you can actually see a bit of what's going on inside. And fortunately I've got one just like this that I've taken apart. It's been in my hands for too long and, well, you know. So, what are the main components of an electromagnetic relay? Well, as the name states, it has an electromagnet in it. So we've got this big coil. Basically, when you supply this thing with a voltage, you've turned this into an electromagnet. Now, another thing that is present in the relay is this thing. It's a pair of switches. Now, depending on the relay, you can have one switch or more. For this relay, there's actually 4 switches inside. Basically, if we look at this, we can see that it has a default state on the right side, and if we would have, let's say, a lever pulling on it, it would switch to the other side. And we do have this relay, and it's pushed by the electromagnet. Now, in the default state, we've got this lever on the bottom, which is open, and when the electromagnet is powered, then the lever is pulled and it pushes on the switches. So basically, this is what a relay does. In its default state, it is contacting one side of the switch. When it's activated, it's contacting the other. So what's this thing useful for? How do you turn this into a power supply? Well, any power supply requires a switch, and an oscillator, and some other components, of course. Now we have the switch. We've got it in the relay. So where do we get the oscillator from? Let's try and build something. So I've built this little circuit. And basically what I've got here is the relay. I've got its coil, the switches. I'm using a single switch this time. And when the switch is in the default state, then the relay is being powered. So we can get current going through the coil, through the switch down to ground. Now, since the coil is powered, it will move the switch to the other side, therefore removing power from the coil. At this point there will be nothing there to keep the switch on the other side, so it will come back, again powering the coil, basically creating our oscillator. And of course I've added this freewheeling diode to prevent any high voltage spikes being created from the inductor. So let's try this circuit out, see if it actually works. It works. You may hear a very annoying buzzing sound. It sounds like a cat has some problems. But let's see how this thing actually oscillates. So we can definitely see that there's an oscillation going on, but we can also see that this oscillation is not a very stable oscillation. So the frequency is not stable, depending on how I'm holding this, or the mechanical vibration going on is changing things. Also, if I zoom into this oscillation, we can see that there's not a single clear square wave, but rather a bunch of these. This being caused by bouncing. So the contacts are bouncing and not making perfect contact the first time. So maybe there's something wrong with this relay. Maybe it's broken or something. Let's try and see if I build a similar circuit, if everything works just like this. So this is the exact same circuit. It's making a different sound. This is a cat that had too many cigarettes, I think. And now if we look at the oscillation, we can see that it's at a bit of a different frequency, different intervals, so it's completely irregular. Now, it's oscillating, so you could build a power supply from it, but you need to rely on a duty cycle that is not constant and the frequency that is not constant. Now, in order to create something a bit more stable, I try to combine two of these relays. See how that goes. Basically, I've built this circuit. So what I got here is two of these relays with the respective flywheeling diodes. And what's special about this circuit is that the relay on the left is being powered through the relay on the right, and when the left relay switches, that's when it will supply the right relay, turning off the relay on the left side. So let's see how this thing works. So it's a bit more complicated, but this should also be good. Yeah, I've built a machine gun. Now the frequency is again completely different. You can actually almost see how this thing is clicking. It's moving so slowly. Let's just look at it and see what's going on. It's moving. So we can see that frequency is much lower, but this time it seems to be a bit more stable. Also the duty cycle is almost stable. This might actually be a usable circuit. So yeah, making it more complicated makes it a bit better. Now before attempting to actually build a power supply, let's just go back to the old books. Maybe I'm missing something. This isn't really the most reliable thing. Or is it? Let's just see how they used to do it back then. So this is what one of these vibrate relays used to look like. Unfortunately, I don't have one of these at hand, since I don't really own one, but I've got this nice schematic diagram to show you. So this is a bit different than the relay that I've been playing around with, in that we've got the coil on the top side, we've got the lever going down through the device, and then on the bottom side we've got the contacts. Now what they tried to do with this arrangement is create a system in which you maximize the time that the contacts are actually in contact and minimize bouncing. Normally you have two pairs of contacts plus a third contact that is normally used to power the coil. So how would you use one of these? What would be some typical schematics for such a circuit? Well, we got here three very nice and very interesting examples. The first one, we're supplying the circuit on the top side. We've got a bunch of filtration. Back then, high capacity capacitors were quite rare, so here there are 100 nanofarad and 500 nanofarad capacitors used. You've got your vibrator circuit. There's no diode over the coil, since diodes were expensive, but you have an RC filter, and then the vibrator is again going through a bunch of filtration and supplying a transformer. So basically this first circuit takes a DC input, turns it into an AC output. Since the frequency at which this thing works is so low, you can actually get this arrangement and basically create 220 volts or 110, depending on what you need. Now in the second schematic, they're actually turning a DC voltage into a DC voltage. But the amazing thing about this is that again you can see no diode. Basically again you're using the vibrator to drive a transformer, but the output of the transformer is not directly connected to the output of the circuit, but rather a form of active rectification is being built using the vibrator circuit itself. So what you're doing here is taking the positive half wave, running it through the top circuit, creating a positive voltage, and creating the negative half wave to create a negative voltage. Again, not using a single diode. Now the third circuit finally has a diode, but this time it's in the form of a vacuum tube, since these were much more common than any sort of semiconductor diode at that time. And this basically takes an input voltage, takes it through a transformer, and then uses the vacuum tube to rectify it by building a full wave rectifier, filtering it and outputting it. So this seems simple enough. I mean, how hard can it be to build such a circuit with the relays that I do have around? Let's try and build something that actually creates a higher voltage from an input. So I looked around to see some typical schematics. And one implementation you can use to create a boost circuit looks something like this. So you need a double switch relay. First switch you're using to create the oscillator, and the second switch is used as part of a typical boost circuit. So you've got your input voltage, inductor, switch to ground, and then diode and output circuit. Now the problem with this circuit is that since the switching frequency is so unstable, you might end up short-circuiting your supply to ground through the inductor and the switch, and that could damage your relay. Now I found that there's an even simpler way of creating a booster with relay by using the relay inductor as your boost inductor and the flywheeling diode as the output diode. Basically something like this. So you've got your input voltage, an input capacitor, 100 microfarads, doesn't really matter, a relay, output diode and capacitor, and that's it. And that's exactly what I've built right here. So I've got my tiny little circuit, I've hooked it up to a power supply on the left side, milliamp meter, voltmeter on the output, some variable resistors, and also the oscilloscope is looking at the switching node. So let's see how this thing works. So we can see that it's quite noisy, and we're making about 55 volts at 0.3 milliamps. So it's not making a lot of current, but if we change the value of the load, we can see that voltage is decreasing, current is increasing, frequency is changing, and also the sound is changing. So we can create a horrible musical instrument like this. Now there's another thing that... There we go, now it stopped. Now there's another thing that we can try, and that is use the double relay approach. Basically, no longer rely on an unstable self-resonating oscillator, but use the double relay oscillator and then use an extra pair of switches as part of a boost circuit. This should create a much more stable oscillation that is not so load dependent. So let's see how that works. So the setup looks a bit more complicated this time. I've got the two relays, I'm using a transformer as an inductor, so I'm only using one of its coils, I'm not using any of the secondaries. And then I've got all my components wired here, so this massive wiring. And let's just see how this thing works out. So we can hear the characteristic machine gun sound. We're seeing a much higher voltage this time. And what's interesting is that even if I add any sort of load, frequency doesn't change. So this thing is no longer load dependent. It's much more stable, much more reliable. Still extremely inefficient, but hey, it works. Now, one of the things that you might notice, something that's not very healthy for the relay, is all the sparking going on in the contacts. The higher the voltage that you're working at, the stronger the sparks. So if I add a very small load, so have some high currents, the sparks disappear. But when I'm working at high voltages, then these sparks are appearing. So this is something that will not keep my relays working for a very long time. So at one point the contacts will oxidize. Finally, the noise has stopped. Now, while on the subject of high voltages, there's an important thing to mention. So this sort of circuit can create quite high voltages. So you really need to be careful not to electrocute yourself. Or even worse, ruin your equipment. So just please be careful when working with high voltages. So why are these things not around anymore? I mean, what happened to these? Well, an answer to that can be found in this table. Basically, what we have here are some Russian-made, Soviet-made vibrators. So we got about 15 of these, and with various parameters. Like what's the voltage at which they're supplied, how many turns does the coil have, what is the resistance of the coil, how thick is the wire, how much current is the coil using, so nothing really interesting until this point. This is where it gets a bit sad. Next parameter is how much time is this thing guaranteed to work. And we can see that this sort of mechanical vibrator can work between 500 and 900 hours. Now, a typical vacuum tube has around 5,000 hours of lifespan, and modern semiconductors have in the order of tens of thousands or hundreds of thousands of hours. This thing will break after 500 hours. The next parameter is again not something that is giving us too much good news. Basically, it's telling us how efficient can we build a power supply with this. And again, we can see that it's somewhere between 50% and 70%. Now this is mainly because of the huge inductors that are being used. I mean, the problem is not the inductance, but rather the resistance of the coils. Also, we have a lot of losses through the contacts. If you're using this thing also to rectify, then it's even worse. So you can make some very inefficient power supplies like this. Even in this book, so this is from the 60s, the very next chapter is about how we can build such high voltage generators with transistor circuits. And the very first thing that they're saying is that transistor circuits are better. Use that. Don't use this electromechanical contraption, since it's unreliable, inefficient, and, well, it's huge. So all in all, hope you got some useful information out of this. Leave your thoughts in the comments. Thank you for watching. Let me know if you actually try to build one of these, and hope to see you next time. Bye bye.